Hi there and welcome to Learn Science. And so today we're going to do a past paper review of chemistry, separates, higher, the November 2021 paper, which is when it was released, and it's going to be paper 2. Now, to use this video effectively, please make sure you pause and try the questions before we go through them. So let's get on with question 2. The first thing, as always, is we go through and we highlight as we read. So we've got the concentration of a solution can be calculated by using the equation, and we have the equation below. So I've chosen to highlight concentration and then choose to highlight my numbers. So in a maths question, always highlight the numbers. It just helps you kind of gauge what you're working with. So we've got 9.25 grams of ammonium chloride and 200 centimetres cubed of water in the solution. Now the first thing I'm going to do is check the units. So we have grams, and we have centimetres cubed and dm cubed. So we need to change that. So we need to go from centimetre cubed to dm cubed. Now it's 1,000 centimetres cubed for every 1 decimetres cubed. So to get from 1,000 centimetres cubed to 1 decimetres cubed, you need to divide by 1,000. So we're working with 200 centimetres cubed. Divide that by our 1,000 so that we have it in the correct unit. And we've got 0.2 decimeters cubed. So that's the volume that we're going to be working with. We know that the equation is concentration equals mass divided by volume. We've just worked out the volume. We don't need to do anything with our mass because it's already in grams, 9.25 grams. So we can just put these numbers into a calculator now. All we need to do is 9.25 divided by 0.2, which gives us our total of 46.25 grams per decimeters cubed. Double check, that's the units that we're working with. There is no mention of any significant figure, so I would just go to 2 decimal places. So in our mark scheme, you're actually allowed it just 46, which is quite surprising. So I would always make sure I would always put in them 2 decimals. But you could have done it one of 2 ways. We chose to do it the first way, which is where you convert the units first. Personally, I would always do that. However, there is the alternative of doing the formula first and then dealing with the units after. So it's up to you which way you prefer to do it. As I say, I would always go units first because then I can just concentrate purely on the maths, knowing that my units are all good. This question is about dissolving ammonium chloride in water and talking about it as an endothermic process. Up the side of the graph we've got heat energy, and along the bottom of figure 2 you've got progress of reaction. Now whenever you see a reaction profile, I would always advise writing reactants and products. It just keeps you right. The first question in this is explaining how this figure shows that dissolving ammonium chloride in water is endothermic, and then complete a reaction profile and label the activation energy. This question, in other words, is asking us to explain what an endothermic process it is and relate it to our question, so our dissolving ammonium chloride in water. So there's 2 types of heat energy that we need to know about just for GCSE. So we've got endothermic and exothermic. You can tell which is which by if it's heat going in or heat going out by the beginning of the word. So endothermic stands for enters and exothermic stands for exit. So heat energy goes in or out. So because we're looking into endothermic process, we're looking into heat energy entering the system. So our exam question and our answer is going to relate to the endothermic process. Reminder that endothermic then is when the products have more energy than the reactants. And you can tell that from the graph. Okay, reactants have lower heat energy, products have higher heat energy. So we're going to want to talk about this in our answer because this is explaining how figure 2 shows that. Okay, it's in that heat profile. So on the side where it's got heat energy, we've got that heat energy has been taken into the reaction or taken into the system, and therefore the heat energy increases because it enters from reactions to products. So hopefully you had a go at that answer there. And here is the mark scheme. So you need to talk about the products have more energy than the reactants for 1 mark. Heat energy increases for another mark, and therefore heat energy has been taken in for that last mark. Obviously it's only worth 2, so any 2 of those 3 would have mattered. Now it is AO3, which is an application question, so whenever you see, well, you won't see it that it's AO3, but it basically means you need to refer to the question in your answer. For the second part of the question, it wants us to complete the profile. So we know it's endothermic, we know heat energy is taken in, so we're going to draw our line there, and then we're going to label activation energy. Remember that activation energy is the minimum level of energy required for a reaction to take place. Now, this is kind of a bit of memory. You should have seen these graphs before. It's endothermic, it goes this way, and that activation energy always does a little bump. You always need a little bump there for the activation energy. Think of it like a hill. You've got to roll the ball over the hill, and once you get that ball over the hill, it rolls down nice and fast. So there is our mark scheme for that. You get 1 mark for doing the line, including the little bump. You need to make sure of that bump. If you didn't have that, you wouldn't get the mark. And the second one is for labelling the peak as being activation energy. So this question wants to investigate whether electricity can pass through solid ammonium chloride and through ammonium chloride solution. And then it shows you figure 3 and how they would set that up as an experiment. So we've got solid ammonium chloride and ammonium chloride solution. Straight away, that's ringing some alarm bells for me and what I'm going to be talking about. If an electrical current flows through the circuit, the lamp will light up, and then it wants us to explain the results of the investigation. So we've got solid ammonium chloride did not light up, and the solution, the lamp did light up, and we need to explain these results. So remembering that word whenever you've got an explain, remembering the explain is when we need to say, well, what are the results? And then why or how. So you need to make a point and then justify it, then explain it, if you will. So what are the results? We have that the solid did not light up and that the ammonium chloride solution did light up. Therefore, what that must mean is that solid ammonium chloride did not conduct the electricity, whereas the ammonium chloride solution did conduct electricity. Okay, otherwise there would be no lighting up. So that would be our sort of first point. That's what the results are, and we know this because it literally tells us in the table. We just sort of have to change it over that no electricity means no light. That's for our first bit. We then need to go on to explaining a little bit now for the next 2 marks. So let's look at why that happens, why the solid doesn't conduct electricity but the solution does. So you've got to think back to structure. And remember, in solid is that you've got all the particles, they are all really tightly bound together. They're not moving. And in this case, because we've got ammonium chloride, we're talking about ions. So we've got an NH4 plus ion and then chlorine minus ions. However, in solution, these ions, same ions, NH4 plus, Cl minus, are able to move around. Okay, so that's the key difference here. Solid can't move, these ions can't move, solutions can move. Okay, so again, there's our difference. Now, all of them circles that I've drawn will represent ions. I just haven't filled them all in. Just to add on a little bit more than that, just sort of in writing form, I guess, rather than diagrams, is that both solid and a solution of ammonium chloride are made up of ions. And then hopefully you can remember that ions or anything that has a charge, so it can be positive or negative charge. Both of them are ions. 3 plus, 2 plus, 1 minus, they're all ions if they've got a charge. So back to the point of the question, which is to conduct electricity. To conduct electricity, a material, if you will, needs to have 2 things. The first thing needs to have ions to carry that electric current. It needs to have positively charged or negatively charged particles. The second thing is that the ions need to be able to move. Now, whenever I see a question on electricity, I'm writing these 2 points, okay, no matter what the question is asking me, and I'm likely going to hit the marks here. So just to conclude sort of everything that we have said so far is that we've got ammonium chloride solution can conduct electricity because the ions are free to move. So this question is worth 3 points. 3 marks, which means we're looking for 3 points. So we're going to structure it like this. We're going to have our first point is what are the results? That's the bit you need to relate to the question. Second bit, we're going to talk about ions. The third bit, we're going to talk that ions can move in solution, but not when they're in solid. I would always sort of say it both ways, okay? And then then last 2 points are always needed to conduct electricity. So going straight through to the mark scheme. Now we needed to say that ammonium chloride solution conducts electricity and solid does not conduct electricity. We then needed to talk about ions, and then third point is that we needed to say that ions can move in solution or they can't move in a solid. You must refer to both solid and solution for full marks, okay? So always just kind of don't assume that the examiner knows that you know the reverse. Always just write in the reverse, especially if you know it, why not? Third bit is, again, it's AO3, which means it's application, which means you must refer back to the question, which if you look back at the first and second point in particular, they